Today I'd like to talk about some of our recent work when we use some machine learning, particularly neural nets, for some of the computational chemistry applications. So when I look for the, well, first, let me acknowledge it's collaborative work, collaboration in my group at UNC, University of Florida, the group of Adrian Neuberg, lots of folks from Yaroslava, and of course, the funding from NSF and ONAR, and we use a lot of compute resources. So none of the work would be possible without their support. So when I look up, for this data science program here, and I realized that most of the people here are interested in inorganic chemistry, but when I was invited by mostly soft matter people, I was asked to do more about organic soft matter stuff. So I'll just quickly mention a few things what we've done with inorganic crystals, and then if something resonates, I'm happy to discuss details afterwards. So my group is part of the AFLO consortium. So AFLO consortium is one of the high throughput compute initiative. It's led by Professor Kurtarol at Duke, again not far from here, and basically what we've done, AFLO is a gigantic database of about 2 million data points. Those are structures of real inorganic and hypothetical materials, as well as computed properties. And in particular, we developed a set of machine learning tools how to predict their properties. So very briefly, this is not focus of my talk for today, but just show you a couple of examples. So what we did, we published last year a paper how to predict some of the thermomechanical and electronic properties with machine learning. For example, you can predict some of the elastic, like bulk shear modulus, the by temperature, and thermal expansion, like that. And again, so those are calculated with DFT versus predicted with machine learning. But what's the very important here, despite the fact we feed our model to DFT data, so when you do this, it's probably hard to see. If you do this three-dimensional comparison between actual experimental data, DFT calculation, and prediction, and you do all kind of statistical analysis, actually the accuracy of machine learning prediction is statistically accuracy of them is statistically the same as the quality of DFT. Right? So essentially, after you invest in these gigantic databases, now you can do very reliable prediction of inorganic materials with machine learning. And also we've done some development of different representation and fingerprint on inorganic materials based on the band structure, for example, and for example, visualize maps of the chemical space of materials, identify certain hotspots of the properties. And for example, what we also did, we can do a materials design where, for example, we worked with the group of Jim Cahoon at UNC in chemistry, who is interested to develop some dye-synthesized solar cells. So what we did, we actually mined AFLO and find the replacement of nickel oxide using some of the informatics tools, and again, it's been published in the last year. Now, as you might see, and it's probably the topic I just described, and it's probably why I'm here. Is essentially we really interested in machine learning, particularly in many chemical sciences, and that's been the focus of my work. So instead of rigorous solving Schrödinger equation, now we can prefer machine learning. So this year we published this perspective overview in Nature, which describes application of machine learning in material science. And if you take the kind of bird's eye view on the development of different computational methods in chemistry, you can kind of think types of questions we want to address and split them in three tiers. So you can think about the first tier as the structure property calculation. And those are really bread and butter of standard computational chemistry. When given the structure, we use some kind of local optimization algorithm. So you have chemical geometry of your system, so this local optimization, and you calculate certain properties. So you connect structure to a property. Now we can challenge a little bit and think about the composition to the structure property relationship. And the example would be a challenge of the crystal structure prediction. So for example, if you draw your organic molecule, just a sketch, can you predict a crystal pocket of this molecule? So that would be example of composition to a structure problem. So the type of algorithm we use here is typically global optimization. It can be genetic algorithm, some other flavors. However, you can even go one step further, and given any chemical data or physical data, we can use various types of machine learning to predict both structure and properties and the compositions. And again, so if you're interested in kind of the overview of the machine learning and chemical sciences, I recommend you this video. Well, so what we've done, probably in this room I should not go into much details, but that's why we have all these big machines, the supercomputers in this country. One of the equation, the fundamental equations, time-independent Schrödinger equation, partial differential equation, and for any practical system, basically you cannot solve it analytically, so you have rely on certain numerical approximation. However, when you steer this equation for a little bit, you can rearrange it and kind of swipe all this complexity into this magic function f, and basically your ground state energy will depend on some input vector of your molecular or materials coordinates, and basically all complexity is this function f. And if you're into machine learning business, you can tell, this is a regression problem, right? So this is my magic connection of the feature to my y, right? So this is exactly what we do. So we use mostly neural networks. We feed molecular geometries, gets the energies, and since neural networks are differentiable, right? We can get the gradients on the atoms, right? They can get forces. You can do geometry optimization, molecular dynamics. You can calculate all other intrinsic properties. Now, for past couple of years, we've been developing this ANI deep neural network, and basically that's one of the first and early examples where we can really push the boundary, and we can show the applicability of this neural network is extensible far beyond the training data to a much larger molecule, and I'll show you some details how we do it. Now, why ANI? So this is ANI. And given proper training, basically we want to train a Padawan network to become a DFT Jedi Master. But hopefully, no one will be hurt during this venture, and we will see how it goes. And so one of the way why we think it's useful is when you think about the hierarchy of different computational methods and plot this kind of cartoonish representation when you have the cost or scale of your computational methods versus some kind of metric of accuracy. We can debate what's the exact metric. For example, so the force fields, if you're interested in simulation of large system, mesoscale things, basically you have to rely to some kind of force field because they're typically linear scale. And the problem with force fields, it's very hard to make them transferable and systematically accurate. And if you ever fit it, your custom residues, how painful it is. So then you have some kind of semi-empirical methods, type binding methods. It's typically, smaller, system, but you may expect high accuracy for them. Then you have, Hartree-Fock, density functional theory, post-Hartree-Fock, and couple cluster would be like gold standard for standard organic molecules. However, you pay the price, the scale and 7 power of the system. So what we try to achieve very ambitious. So for our work, we pick a particular combination of hybrid density from DFT and a particular basis set, and we train, to this. It's our choice. It may be, not the perfect choice, but we make a decision at the level of theory we use, and we aim to shoot for this top left corner, and we would like to maintain this accuracy of the underlying. Of course, we cannot beat it, right? Because we fit our model to this accuracy, and we want to be fast and accurate, so we want to shoot to this corner. And just, I'll show you a couple of progressions. For past year, the pace of, changes in this field is tremendous. So for under a year, so first we use, different techniques to improve the accuracy. For example, we use active learning to expand, chemical space and, do more optimal training. So we can increase accuracy a little bit, but also we start working with the post-Hartree-Fock methods. In particular, very recently, we train one of these neural net potential to the couple cluster CBS data. So we also make steady improvement in this corner. Now, how this work? If you're familiar with standard, machine learning workflow, it's practically the same. First, we craft some kind of training data, in our case, is molecules. If we think about molecules, we, as a chemist, or represent this data as a Cartesian coordinates. But since all molecules, different sizes and shapes, this particular representation is bad because neural network, require, or all machine learning per se requires, the input representation, be translation, rotation, and variant, have to be constant size. So, about 10 years ago, Weller and Parinella introduced the idea of so-called molecular, atomic environment, where you transform Cartesian coordinates essentially into spherical coordinates, atom-centered spherical coordinates, and every atom represented by environment, and basically this representation satisfies the requirements, feed them to neural network, and we use some kind of error function and use backpropagation to train these things. In the original representation, it was developed for silicon, which is very homogeneous, very easy material. This representation is not expressive enough for organic molecules. So in our work, we modify the mathematical form. If you're interested in specifics, it's in the paper. But idea is the same, still atom-centered. We just modified the exact mathematical form of this representation. So essentially, this new molecule, what's happening, so your neural network essentially zoom in on each of this environment, and your total energy would be essentially some of these local energies. And again, so it's really not a magic. So you have a lot of your training data. Basically, you calculate environment for each element. You pass it through neural network. You sum this fake local energy to total energy, which is DFT total energy, and basically you train this end to end. So you never touch this stats. Now, the ugly part of this approach is extremely data hungry. So the database we run currently lists over 25 million data points for DFT calculations, small organic molecules. It's all available, so if you're interested, it's on GitHub. All the software is available, and basically, again, we use standard, kind of statistical approach when we train on part of the data, validate on separate data. But then, when you want to test what's...
So what is a data point? Is it a geometry?
It's a geometry.
A composition?
It's a three-dimensional...
All of these?
Yes, it's a particular geometry and corresponding DFT energy. Those data points do not only correspond to a geometry minima, since we're interested in the potential. So most of these points are off equilibrium geometry. And we use a certain sampling technique to get them using normal modes. We perturb geometries along the normal modes. So essentially you probe the curvature of the potential energy. Now, when you think about the application of these things, what's been done in typical computer science application is you may test your potential on known science molecules. For example, in our work, because this number is so high, we calculate mostly small molecules. And we rely on the idea that chemistry in semi-local, if you look this small atomic and molecular environments, you may extrapolate to certain degrees. However, what's been standard practice is what's called interpolation. So if you train, let's say, to a system to 8 heavy atoms, you may test it to different molecules that have 8 heavy atoms. However, for us as a chemist, this is not very interesting. There is not many molecules with 8 heavy atoms. So what I will show you next, and all of my examples, when we tested on unknown sizes, this means larger, molecule larger than we trained. And this is a distribution. So this is the density of our data. This is number of heavy atoms and total number of atoms. This distribution in blue, this is our training data. And then we tested on larger system from real life example. For example, drug banks. Those are large system from FDA approved drugs. And again, so the sizes are more than 100 atoms. We also constructed some tripeptides, which again, larger than there are sort of a couple of examples from those benchmarks. Again, it's published, it's all open, all this data is available. You see the standard kind of drug-like molecules, greasy molecules. But also, we crank up the challenge. Whatever we can do single point DFT calculation for small peptides, those are 300 atoms. We also include them. So this is really pushing the limit how high we can go. Now, one of the challenges with machine learning methods as we treat them as a black box. And often as a chemist, this is not very satisfying because you have to know, can I trust them? Otherwise, this is yet another instance of the force fields, just without explicit functional form. So what we use ideas from active learning. And for example, we can use ensemble we can train ensemble of our neural network on different parts of data. So it's we initialize training with different seeds. So you can probe the disagreement between the prediction. And so let me show you an example. So just for illustration, I'll show you we trained 3 different neural networks, and we estimate a prediction of some quantity, some kind of phase space. And what you can mention here, that in certain regions this prediction agree, certain disagree. What you can do, you can go back and run your QM calculation. And what we show in the paper published this year, and what people show in application in different domains, basically when the ensemble is an agreement, we have a good coverage of the data. And when there is a bad data coverage, basically neural network give you predictive all over the place. And basically this ensemble disagreement is very nicely correlated with the error versus DFT. So what it allows us to do is first to understand where we can trust those predictions, where we overfit, where we don't have a data coverage. But also it's really good news for our students, because we can do fully automated, self-consistent parameter generation scheme. So you run a script, and basically you keep drinking coffee. You don't have to do much. So what's happened here? So we train ensemble of our neural network. Then you throw a kitchen sink of your data sources. Can different reaction, different molecules, whatever you want. So then we probe through this ensemble disagreement, and we establish a certain criteria. If the disagreement above certain threshold, basically you put it to the queue, you run your compute cluster, in the compute cluster, all your DFT calculation, you update the database, retrain the ensemble, and basically this loop is fully automatic. And it allows us to very rapidly expand the applicability, to different chemical spaces and for different systems. And also, this is not very, in contrast to a fitting force field, this is much less laborious and tedious job. Other advantage doing active learning training is it much more data efficient. So when we published a paper in 2017 again, this is our benchmark for this large realistic molecules. So when we calculated over 20 million data points, the accuracy was not that impressive because this data was selected randomly by us, essentially. However, if you do this active learning training, so what we did, we revisited, we trained using active learning, and by the 2 million data points, you essentially exceed the original accuracy. So you're 10x data efficient, and by the 5 million data points training, basically you reduce this error fourfold. So this is much more data efficient. And then again, so this improvement are universal in total relative energy, in the force prediction. So everything gets better. So this is really the way to train those data-driven. And again, it's been published really. Now, let me show you a couple applications. Since we're interested in molecular simulations, in particular molecular dynamics, so forces really very important, very key. And to put this in perspective, so this is, the forces you will get from any potential active learning train versus true DFT forces. And so the accuracy is 4.2 kcal per mole per angstrom. And the scale, keep in mind, the scale is actually exponential. So essentially all points sit here in the red. And there's just a few outliers. And if you compare with popular semi-empirical method, for example, tight binding or PM6, basically it's a twice or 4 times larger error. So you really get very high accuracy forces for simulation. In addition, you can train different properties. For example, recently we tried to predict, partial atomic charges. And what's interesting, what we did, so partial atomic charges are not physically observable things, right? That's why we have all these different schemes. They're always conflicting. They have a lot of different problems with them. However, the molecular dipole is directly observable. So what we ask our neural network, okay, can we reconstruct a dipole and learn charges that would fit to this dipole? So in other words, so my neural network will reconstruct partial atomic charges that would correspond to DFT computed molecular dipole. And we don't tell it any restrictions. In principle, your charges can be anything, 20, 50,000. However, what's happened, and we call them ACA charges. What's happened, the neural network essentially reconstructed so-called CM5 charge model 5 scheme, which is actually type of the Hirschfeld partitioning scheme fitted to experimental dipoles. But again, first of all, we reconstructed it unbiasedly by neural network without any hand tuning and and work. So we can, and basically now neural network can very nicely, predict your total dipoles. We'll get nice charge scheme which is consistent with CF5. What is also interesting, we didn't constrain the quadrupole, but we get very nice prediction of the quadrupole moments at all. And what this scheme can give you, essentially, if some octopoles are very important for you, you can use this approach and use higher moments and get your quadrupole consistent charges and other things. So now, as we can predict energies, we can predict forces, we can predict, for example, charges. We can put this all together, and now machine learning can run your simulation. You get energy and forces, you integrate your molecular dynamics, For example, at that frame, you predict charges, you predict dipole, and basically you can do time domain machine learning and predict everything. And for example, you can compute IR spectrum. So this is what I show you, several organic molecules. When we run molecular dynamics with our force field, construct dipole, do dipole velocity, the correlation function, and construct the IR spectrum. It's in red. What we did, it's kind of expensive to run ab initio MD and calculate that. We cheat a little bit. We calculated harmonic frequencies and multiplied by certain width, and basically you get spectra in black. But you can see you have very nice, correspondence. You see peaks where they should be, and again, this is very fast. And everything is done on the fly with machine learning. Now, can we go beyond DFT? Because for certain applications, you will say, yeah, DFT, you run 10 different functionals, you get 10 different results. Can we go beyond density functional theory? And that's been busy summer for us. And as I told you in the beginning, so coupled cluster theory is extremely expensive. So definitely we can, since those methods are data hungry, we cannot do straightforward conventional coupled cluster unless you have the Bitcoin mining farm somewhere in your basement. So we have to be smart. And the way we think about it, so if you're familiar, with the, basically the gold standard for the organic thermochemistry, it's called, coupled cluster with, with triples and extrapolation to a complete basis set. So the energy is basically the Hartree-Fock energy term with CBS, MP2 with CBS, and then you do the trick of the, you run coupled cluster with a relatively small basis set and do correction between MP2 and the coupled cluster. So this is one of the standard extrapolation scheme. So basically this term, when you do coupled cluster simulation, is extremely expensive. However, recent development in the coupled cluster theory, there are approximate coupled cluster methods called TLP-NOM, pair local natural orbitals approximation. And basically, what we elaborate in this is this paper on the Chem Archive, that we can approximate with very high accuracy this term with the approximate coupled cluster calculations. So you see the star here. So this is what we did. So this is the one. This is the trick, and you see the scaling, right? So if you calculate the alanine, so this 13 atoms, it's 9 hours. It's not bad. You go to aspirin, 21 atoms. So it's a still small molecule, but it's already 400 hours. So this scaling kills you. However, when you use approximate coupled cluster, basically you drastically reduce the time scale. But the errors didn't change that much. So this is the first part. Now we can do reliable, high quality, approximate coupled cluster, and now we can scale them. We still cannot do millions of them, but we have another trick in our sleeves. And again, so in the machine learning, you can transfer learn from one domain to another domain, which is called transfer learning. So we can take advantage of all our DFT data. We should not throw it, because it already gives you a very nice approximation of the potential energy surface. So now we have to learn how to combine multiple levels of theory together. And again, ideas transfer learning is very simple. I think it's very clever. So first, you use your chip, which in our case DFT. You train your neural network to your chip approximation. Then you copy all your weights to your expensive domain. In our case, this coupled cluster. then because number of data points in our couple cluster is smaller, we fix part of our training parameters in neural network and change only the top layer. And you retrain this neural network with the couple cluster data. And basically what we show in this paper result in kind of a Frankenstein energy functional, in many cases is indeed exceeding accuracy in DFT. So let me show you a couple of examples. So for example, this hydrocarbon reaction energies are surprisingly difficult for DFT, or not, because they deal, for example, isomerization of this, three-dimensional caged hydrocarbon to this kind of aromatic system. It deals with the formation of these double bonds that have higher electron correlation, and that is hard problem for many DFT. So, and there are several of these reactions, which we get from literature. And what you can see here, so basically this is a reaction, and this is the error. So in red, this is our DFT functional we use. This is our neural network trained on DFT. And what you can see here, the errors are terrible. You get 15, 40, 30. Those are terrible errors in reaction. If you off by 30 kcal, it's a disaster. However, when you retrain, or both couple cluster, of course, quite accurate. But if you retrain, this neural network is extra couple cluster data, you drastically reduce error for them. And again, none of the system were in the training data. We did the same for different isomerization reactions. For example, the sugar cyclic to open, and basically the story is the same. So DFT have higher, very large errors, 4 to 8 kcal. And we run several other different benchmarks, so I will not bore you with more technical details. But what's also relevant for colleagues in my department and some of our other work in the drug discovery. For example, if you're interested in structure-based drug discovery, so you're interested to find the three-dimensional geometry of a particular molecule, and here the ranking of conformers are looking for dihedral profile. So dihedral, if you rotate molecular moiety around one of the bond, so you have this dihedral profile of energy. And that's very important if you want to find some different three-dimensional conformers. And basically, there's a very nice paper published last year from Genentech. Basically, they will calculate very large number of these drug-like molecules and calculate all different flavors of these dihedral profiles. And they score whole slew of different methods, starting from some of the commercial force fields, open force fields, some of them standard Amplitude calculation, different DFT, and so forth. And then what we did, we take this data set, this benchmark, and we see where we are currently. So when we do training in the using DFT data, we are somewhere here. So basically, we better than any force fields you can think. However, we trail popular DFT functions. But if you reach, if you add this couple cluster data, you exceed any DFT functional. Here I just list you couple, but in the original papers they have like 10 different. And basically you're approaching this, very expensive, MP2 couple, CBS or couple cluster data. Now.
So could I ask a
yes.
question? Your system is composed of overlapping regions, I guess.
Yeah. And
within each region, you have a set of force fields or characteristics or volumes or something. Now, when you train the system, you're varying the parameters within each of these overlapping units. And the outcome of that is some energy parameter, I guess. And that's what you're comparing with your many electron data.
Yes, I compare, total energy, what comes from your TFT or whatever.
And then if the deviation is not small enough, then you go back to some of your overlapping regions and adjust the parameters?
Well, you can think about it like this, but it's not like you...
I know you don't do it by,
yeah.
by hand.
So if we see if this class of molecules is generally bad, or, it's not even class, like if you never seen sulfur, right, it's naive they can predict sulfur, right? So you have to include, data about sulfur. So what we do, we just include, some molecules that have, sulfur.
And there's no correction for the degree of overlap of the different regions that you're putting together?
There is, no, it's very simple. So the trick with this spherical representation is just to make it convenient for a machine to be as an input. We don't do any, handwork or, tuning of the things, right? So just to transform coordinates into the convenient format for a machine, essentially. Now we, can we go beyond just simple energies and maybe properties? So what we work right now is, can we put more physics in it? So before of that, again, with the exception maybe of the dipole constraint, right? So this machine is essentially a stupid machine, right? So you want to predict just a number. So there is no physical constraints. But chemistry is moving into realm of automation, and machine eventually will have to do some make decisions. So when you constrain, when you put more physics, arguably the methods would be better because you put some real physical constraints which help your machine to make more accurate prediction. What we work right now, we exploring is a very complex diagram, but we exploring more complex architecture for neural networks. And you can think about neural networks as Lego building blocks. And you can shuffle them and combine together in almost arbitrary way. So a couple of ideas. So for example, we can use skip or residual connections between different parts of neural network, which essentially help pass the information between different parts of molecules. So what it manifests in real life, it's a long-range interactions. It helps to propagate information between these environments in kind of larger scale. So it helps you, with kind of like a Coulomb type, the long-range electricity. Also, we work and train those neural networks to multiple different quantities. The advantage of that, you'll get more data for free, essentially. And this data is not random, right? So it's all relevant for electronic structure and properties of atoms. And also, it's very practical and pragmatic because you do forward prediction, and instead of energy, you get an energy, and you can charges and all different things. So it further helps accelerate your simulation. So it's faster and better. And we train this particular neural network been trained to total energy, partial atomic charge at a particular scheme, atomic volumes, and if you know from atomic volumes, you can get quantum dispersion through a many-body theory. So in addition to very good energy and charges, you can get all those properties in one shot. And the skip connection, as I mentioned earlier, it also helped to improve the accuracy. And so this is first, it's our original ANI architecture, which has no these connections. And when you have a couple of these residual connections, basically, it helps you improve accuracy a little bit. And it's interesting, it especially helps in forces, for example. Let me show you a practical example. So, for example, if we have this this compound with a couple of conjugated bonds, so this is sulfur, and if you modulate, for example, a different substituent, and you can vary is it substituent electron withdrawing, donating, and if you run your quantum mechanical calculations, basically you can change this partial charge based on the type of this substituent. It's very well known, in fact, since the sulfur is polarizable. And for example, the size of our atomic representation is about 5 angstroms. So if you don't do this skip connections, so basically for neural network, it's very hard to see what is beyond one of this representation. So with no skip connection, essentially what's happened, there is no information passed from one environment to another. And basically all these charges are the same, which is the artifact, and this is the error in the model. However, when you add these connections, basically you can recover correct behavior and the charges. And again, we check and see, basically you get a very nice comparison with state of the art, with current methods in terms of the energy. But also what's interesting, this type of architecture, if you think about here, it's kind of a bottleneck. So all the wealth of this information that's been learned by a neural network, it's compressed here. So we can take this neural network and we can arbitrarily add different properties. And because we already learned a lot of chemistry, it actually helps you quite dramatically. So what we did, so we asked ourselves, can we take advantage of this information? And one of the, what we thought, okay, we have energies, we have partial atomic charges, we have atomic volumes. If you know how, the continuum solvent approximation is done, it essentially relies on the, the electrostatic surface and atomic volumes. So all of these things are very relevant, and we can learn, the particular continuum solvent approximation called SMD. So what we did, we add an extra, kind of head to predict this, SMD salvation. Again, we use the same DFT functionals, and with 10x less data, we can achieve the same accuracy 1 kcal. So you really, you really take advantage of this kind of rich information here. And what's in practical terms, now we can do salvation for energy, which is very useful for physical organic chemistry. So Chris Kramer and Don Schuler work on, for a long time for this MNSOL database, which basically have about 1,000 salvation-free energies for drug-like molecules. So what we did, we took our neural network. We get this energy of salvation. Now we can back propagate. We can get forces. We can get frequency. We can calculate standard, thermodynamics. And basically, what this graph shows you, this experimental Gibbs salvation energy versus inlet salvation, you get the very nice correlation, RMSD 1.8 kcal per mole. And if you look on literature, basically 1.8, this is as good as difference between two different DFT functionals or two different salvation models, CMD, SMD versus PCM or something like that. So we can get very accurate salvation. Now, let me wrap up with a couple of fun things. This is less quantitative, more entertaining. This is, I think, what we will be in a few years. Now, I can take my model and I can ask, can I do some fun with it? So since I'm in School of Pharmacy, I go to PDB, I take a protein. Conveniently, you know, in current neural network, we don't have all elements, but we have 7. We have carbon, hydrogen, nitrogen, oxygen, sulfur, fluorine, fluorine. So I picked this particular protein which has some ligand inside, right? I cannot do ions yet, but you know, I can set up a simulation. I can I can put this protein in explicit box of water. Cannot do ions. So this is your protein in distilled water simulation. 35,000 atoms. And again, I don't do any retraining. I just see if the simulation what will happen. I set up and I run it. For clarity, I just emitted water, but you see some hydrogen bonds. And this simulation is boring. Didn't blow up. But what's interesting to see, at least qualitatively, we can extrapolate and say, okay, this protein is still folded. There's my ligand here. Doesn't do anything crazy. If you calculate the MSD, it gets stable. We run it for like 50 nanoseconds. It's stable. Okay, that's cool. At least we see that given a little bit of a small peptides data, we can at least qualitatively it learns that the protein is folded. But of course we cannot claim so this accuracy of the your favorite under a chow. But at least qualitatively do it what is happening. And what's interesting, and this is a very hard problem, when the student did the simulation, basically the protonation was done very simply, just run on a server. So what happened, you see this acidic residue, and it's protonated, which is wrong. So in water it should be acidic. But when you run the simulation, what you see, it's deprotonated, and it protonated this actually nearby. So another advantage of this method, they're fully reactive and basically self-error correcting. At least So you can envision that you can do real change in protonation state simulation, which is very important for a function of proteins. Now we can crank up even more. Again, it's the same potential. What we did, let's do some material science. So what I'll show you is about 4,000 atoms. It's a hot carbon vapor. It's 2,500 degrees, so high temperature carbon C2 simulation. So you start from random carbon gas. And what happened, you see formation of this beautiful graphene flakes. There's the formation of fullerene. You see the buckyball. Some of the flakes start wrap. You see formation of some nanotubes and larger graphene flakes. And again, the same simulation, I never refit anything. But what's interesting here, from the isolated small molecules, it can think, oh, carbon might want to be conjugated 6-membered rings. And at least qualitatively, it captures the correct behavior. And again, probably quantitatively is wrong, but at least we see this encouraging behavior. And what also interesting, so about 5-7 years ago, late Professor Marakuma published simulation like that. It probably took them a year on a large machine to run those ab initio empty simulation. Now you can run it laptop in a few hours if you have a GPU. So those are acceleration of and new types of science that are accessible for people. So with that we wrap up a couple of publications. So if you're interested, everything on GitHub, it's a convenient Python library. We have a new PyTorch implementation. If you're into a challenge, please beat our accuracy. The data is all available. Thank you very much.
Any questions?
Could you give me an idea of the fundamental subunits that are entering into your carbon calculation? For example, I could imagine a characteristic of a carbon atom. I could imagine a characteristic of a carbon atom coupled to a couple of other carbon atoms, and so on. How many of these starting units do you have?
we don't have any type of atom. Like in force field, you have sp2, sp1 aromatic carbons, right? So here, if you have carbon, it's just a carbon. The only differentiation for every carbon learned by a neural network from this descriptor. Descriptor is about a nanometer size environment around carbon. And you can think, basically it's encode this character, right? If I'm sp3, I sort of have 4 neighbors, right? At least in the first shell. So this descriptor goes a little bit beyond the first shell, probably like 2 shells. So, and basically it learns what's to be aromatic carbon, right? So you have 2 or 3 members, neighbors. But we don't do anything like handcrafted. We say, oh, this is carbon. Yeah.
But you could do it with a hierarchy of units. Carbon being one, C2 being another, C3 being another.
Yes, but we're going back to the idea of the force fields. And when you start to differentiate different things get arbitrary, right? If you do chemical reactions,
It's a lot harder, right?
it's also ambiguous, right? When you do chemical reaction and carbon change the valency and things get complicated, and you cannot manually label this. If a transition state, am I already sp2 or sp3 or am I aromatic? So I think the beauty of that it's raw data, but we ask a machine to figure out all those things. At least that's my kind of interpretation of that. So what we try to achieve to make our lives easier, to avoid all this, labeling. Or,
The parameters that you're using belong just to the carbon atom.
It's a all sphere, it's kind of environment all around
they
there.
interact with each other.
Yes.
But is the assumption that one carbon interacting with another is the same as a pair of carbons interacting with a third?
Well, inside the environment, you have multiple atoms. So if I'm central atom, I see, many of my neighbors. I think, when you see...
Because of the force field.
Yes, because you feed each of this environment to a neural network.
Is there an excluded volume term like a Pauli term in it? No hard sphere term?
Well, certainly you probably will break things because we never show it, if you put like 2 carbons.
Your potential takes care of that.
No. So if you manually put 2 atoms on top of each other, probably simulation will blow up. But it will blow up in any simulation because when you have 2 atoms on top of each other, things get. Yes?
So in your time domain machine learning simulations, when you were talking about using the machine learning to calculate the partial atomic charges, is that something that can be done throughout the course of the simulation as an atom changes its environment?
Yes.
And that's what is happening in your...
Yes.
Okay.
So all the charges are not static charges. They are instantaneous dynamic charges.
Okay, wow, that's really cheap. And how large of a system can you do that with?
We tried, the problem is it's very hard to compare, right? So if I run organic molecules, I can run DFT. If you run like a single point for a protein, and you will get, accuracy of about 10 to the minus 3, 10 to minus 2 error in charges, which is very respectable. This is the error between basis sets. But beyond that, it's very hard to compare. If you, in principle, if you how much you can, afford, how much memory you have. Again, you run 50,000 atoms, you can calculate. But the problem, how you compare is what.
So, and unrelated to that, what engine are you using to run your MD simulations?
This one was done very simple. So there is a Python library called ASC, Atomic Simulation Environment. It's as free open source. The beauty of that, it's in Python, and all our code base in Python. So the connected to MD engine was So one function. Very, very easy. We're looking, but the problem is that particular software, it's more educational than like Charm or Amber. So we're looking into, connected to probably Amber.
Have you looked at OpenMM?
OpenMM, yeah. So one of the library, but it requires a little bit more development and doing some C. In case of Amber, it's Fortran.
I have a question.
Yeah.
So in your fingerprint region, did you use a hard cutoff? Or?
It's a soft Gaussian, basically. It
Okay.
smoothly goes.
All right, and that goes out to
1 minute.
1 nanometer. Okay, and then after that, you just cut it off.
Yeah.
Okay.
It smoothly goes. Because if you do hard, this thing gets you, has problems with the energies, right? So everything has to be smooth. Right?
Oh, wait, were you talking about the simulations?
Yeah, so in my descriptor, the sphere is not a hard sphere.
Okay, so it doesn't just end after the 5 angstroms.
It's slowly, so since you multiply in Gaussian, basically it kind of dies very slowly.
Okay.
So there is no like, how does my fingerprint done? Go to 0. So it's essentially like a switching, very smooth switching function. If you are working as a first one, the whole switching function.
It's more switch.
Yeah.
So you have about 20 million calculations in your training data set.
Yeah.
If you were to say add, iodine to your training data set, how many more calculations would you need to maintain accuracy?
That's a good question, right? So halogens, we've done fluorine and chlorine. So halogens are easier because typically in organic molecules, unless you kind of doing some exotic chemistry, typically they are near carbon.
Yeah.
So the diversity of things you see with iodine is relatively low. But if you think about like boron, it's like 50 volumes of boron chemistry. That would be hard. So that would depend. What's, so iodine probably less than 1 million. Boron, I would give up probably. Well, you can do certain part of boron, right? But boron is notorious that you get all this. They still invent all those phases of boron. It's like 10 of them every year come up, all those fancy new phases of boron. So that would depend on type of chemistry.
Okay.
And certainly if you think about like metals, right? If they are like sodium, calcium, right, that are straightforward, more or less. So they're typical, they're relatively easier. And in biological environments, they're typically ions. Or think about like iron, cobalt. So you get spin states, so things get complicated.
So in your last carbon simulation, the DFT training set also includes structures that we can see in the simulation like fluorescence and hexagonal sheet, or it's just random perturbation in DFT
Well,
training set?
since we started working with some chemical reactions, so there is some data about bond breaking. But again, all the training data was small organic molecules, and we showed.
So neural network did not see any fluorine structure.
We never trained. Well, it never seen more than 2 rings together. Think about naphthalene or typical organic. So it never seen caranine or small flakes. Never. So that observation was
Interesting.
And but also what's interesting, if you look for uncertainty of this prediction, it's through the roof. But at least qualitatively, you see a right picture.
Any other questions?
Yeah, I have a question about the long-range interactions. How did you implement those? Because I guess in most neural networks, you think all the nodes of one level are connected to all the nodes of the second level.
So if you don't skip residual connection, our long-range interaction is essentially limited by 2. If you have 2 neighboring spheres overlapping, that's as far you can pass the long range in the what I call the 1X. So the
Okay.
long range can pass implicitly through this. What we work right now, since we have charges, we can do explicit long. And then
Okay.
you can do periodic boundary, particle mesh, all these things. With the skip connection, basically number of this skip connection increase your range.
Okay.
And it's kind of like a cutoff, but it's a real space cutoff, right? So we can calculate. So for example, if you have like plus and minus on specific distance, knowing this distance, I know the number of my iteration have to be, or the number of this connection have to be more than that. If you know the scale, the scale of your interaction,
Okay.
we can.
And is that like the layers of the neural network?
Yes,
Or-
through the layers of inside the neural network.
Okay. All right,
Because
so-
essentially each skip connection pass information from neighbors to neighbors.
Yes.
So if you have a few of this thing, it's neighbors of neighbors of neighbors. Basically, you pass it through higher, larger distance.
Okay, so if you wanted to simulate a larger distance instead of having to train a larger network with more layers, then you use that mechanism.
Yeah.
Okay.
Or you can do classical if you're interested in ions. That's probably easier.
And as a follow-up, and do you still use a symmetric function as a molecular descriptor
Yes.
for the same function?
Yeah. They work well.
Yeah.
Any other questions? Okay, let's thank